All right, let's do some examples of box model systems in which we have more than one reservoir. So we're going to start off with a water filling tank example yet again, but this time add 2 tanks. And so in this case, we're going to have a flow in to a first tank, which then flows in to a second tank. And I've shaped the tanks differently so that we can have a more interesting dynamics. H2. So the first tank has a water level H1, the second tank has a water level H2, and the flow in to the first tank is going to be prescribed. So flow in is just R of T. And then the flow out here of the first tank, which is also the flow into the second tank, will be, so from here, flow out of tank 1, which is equal to the flow in to tank 2, is going to depend on the water level in tank 1 and not in the water level in tank 2. So we'll just be lambda 1 times the height of the water in the first tank. And then here we'll have a flow out of tank 2. So flow out of tank 2 will be equal to just lambda H2. And here I'll introduce the parameter lambda 2 H2. And we have 2 different parameters because maybe the size of the drains is different for each case. And then it's just a matter of writing a conservation equation for the volume of water in each tank. So let's assume that the cross-sectional area of tank 1 is A1, so this is V1 is equal to A1 H1, and V2 is equal to A2 H2. And then writing down the conservation equation for the first tank, we have d by dt of volume 1 is equal to flow into tank 1, which is R of t, minus the flow out, which is minus lambda 1 H1. And then using the fact that V1 is just A1 times H1, with A1 to be a constant, we have d by dt of H1 is equal to minus lambda 1 over A1 H1 plus R of t divided by A1. Now we can write down the volume conservation law for the second tank, and we have dV2 dt is equal to, so the flow in for this one is the flow out of the first tank, which is lambda 1 H1, and notice that the sign changes. What flows out of this one with a negative flows into this one, so there's a positive. And then the flow out of the second tank, which is minus lambda 2 H2. And then again, using the fact that the volume in tank 2 is A2 divided by H2, we have dH2 dt is equal to minus lambda 2 H2 divided by A2. So that's the flow out divided through by A2, and then the flow in plus lambda 1 H1 divided by A2. All right, so we can now rewrite this system of equations into matrix form, but before we do that, I want to introduce some new constants to make the writing of the equations simpler. So let's define the first time scale, tau 1, will be equal to A1 over lambda 1. So this parameter, lambda over 1 over A1, as dimensions of inverse time, is the same dimensions as dt. So that's the first time scale. Then there's going to be another one that comes over here from this one, so I'll call this one tau 2, which is equal to A2 over lambda 2. And there's now a third time scale, which is lambda 1, which is A2 divided by lambda 1. So I'll call this one tau 3. equals to A2 divided by lambda 1. And so then the equations become dH1 dt minus, or is equal to minus h1 over tau 1 plus r divided by a1. And then dH2 dt is equal to minus h2 over tau 2 plus h1 over tau 3. And writing this out as a matrix vector form, we have d by dt of the state of the system, which now has two variables, h1 and h2, h1 and h2, is equal to the rate of change of the system, which can be now written as a matrix times a vector. So we'll have a matrix times h1, h2. And now to find out what the components of the matrix are, we look at the first equation. We'll fill out the first row. So the first row corresponds to the first equation. The second row will correspond to the second equation. Or you can view it another way. The first column is everything in here which multiplies h1. So we can fill it out either way. We can say here h1 multiplies minus 1 over tau 1. So we get minus 1 divided by tau 1. And over here h1 multiplies 1 over tau 3. And then if we look at the coefficient of h2, this one there is no h2, so there's a 0. And in this one there's a minus 1 over tau 2, minus 1 over tau 2. And what we're missing is the non-homogeneous part, which is the source term. So plus r of t divided by a and 0, because there's no non-homogeneous source term in the second equation. And so this gives us the system of equations for the two-tank problem. And now I want to solve this equation first numerically using the Euler forward and the Euler backward scheme, and then analytically finding the exact solutions analytically, and then go back and look at the performance of our numerical solvers depending on the analytical solution.